Hey everyone, so today we're going to begin a new chapter, chapter 7, which is the topic of phase diagrams. So in chapter 5 and 6, you have seen the processing of metals and some important parameters like stress and strain, and also um, the failures of metal, which is in chapter 6 specifically. Okay, so in chapter 7, we are going to go a little bit more scientific. Okay, we're gonna go deeper into the materials itself and look at their structures. And in reference to the phase diagrams, we have seen structures in chapter 3 and 4. Now we're going to relate them to this what's called the phase diagrams. Okay, right, so to understand phase diagram, let's first discuss what is the phase and what is solubility. Okay, so looking at these two diagrams, as in it's one diagram, but we have two situations here. One is marbles in water in a glass. The other one is you put salt in water in the same glass. Okay, so of course what will happen to the left glass or the mixture on the left is these marbles will not mix with the water. It will not dissolve in the water, whereas salt will dissolve. But the question to ask is it going to dissolve infinitely? Can you put unlimited amount of salt in this water and it will still dissolve? Of course, the answer is no. Okay, you know that there's a limit for the amount of salt that you can dissolve in water, and that is the solubility. Solubility is limited between two substances. Okay, salt, certain amount of salt in a certain amount of water will give you a certain value for the solubility. Okay, compared to marbles, any amount of marbles in water will not make it dissolve. Okay, so in this case, we can call the um, system on the left as a mixture and the one on the right is a solution. So a mixture is where the parts can easily be seen and removed. They are not dissolved in one another, whereas in a solution, they are still called a mixture. Solutions are still mixtures, but solutions are dissolved in each other. Okay, the substances are mixed, they are dissolved in the other substance. Right, so that's the difference between mixture and solution. Now, how is it related to the level of solubility? Okay, so on the diagram on the left shows a solution which has many solute particles. Solute particles are the particles that you dissolve in the liquid solution, which in this case, the solute is the salt. The solution is the water, or the solvent is the water. The solution is the mixture of both. So here we have solute particles creating two different types of solution. On the left is a concentrated solution which has a big number of solute particles, and a dilute solution has a small number of solute particles. Okay, and the solvent is the liquid itself. Solvent plus solute will give you a solution. Okay. Now, is solubility unlimited? So I have answered this question. No, it's not unlimited. A certain amount of solute can dissolve in a certain amount of solvent under certain conditions. Certain here means that there's a specific limit, specific value. It's not unlimited. So what happens when you reach maximum solubility? Which means you are pouring salt into this water. What happens when the most amount has been dissolved, and then you keep putting in salt. What happens is you will see salt particles, solid salt particles here, collecting at the base. This is already a salt solution. And then you put in more salt, you will see the solid salt gathered at the bottom. So in a way, you are already forming two different phases in this mixture. There's a salt solution and there's a solid salt particles at the bottom. Why? Because it cannot dissolve anymore, because it has reached maximum solubility. Okay, so how do you want to prevent this? I do not want to see the salt particles here. Of course, obviously don't put it there in the first place, but if it is already there, there are a few things that we can do, which includes heating up the solution or stirring the solution to increase its kinetic energy. You have probably done a similar experiment in school, yeah? Okay, the last question here is, what are the factors that affect solubility? Okay, of course, in terms of the saltwater solution, the factors that affect it would be the temperature of the solution, the amount of salt, the amount of solute particles that we put, or the amount of solvent that is there. Okay, these are some of the factors. Now, let's look at a graph. Okay, because this chapter is about phase diagram, so now let's look at a phase diagram. This case is very relatable topic, I would say, because it's the solubility of sugar in H2O. Okay, this is sugar, this is water. So the graph, let's get familiar with the graph. On the y-axis is temperature of the solvent. On the x-axis is the composition, how much water and how much sugar is there in the mixture. Okay, so how to read this axis is you will have either one or both components. In this case, it's sugar and water, and they are inverse of each other. If there's 0 sugar, of course, it's 100% water. If there's 20% sugar, there's 80% water, and over at the extreme side, if it's 100% sugar, of course, there's 0% water. Okay, so this is how you read the composition axis. It's in weight percentage. Weight percentage means total 100 grams and then divide it accordingly. 20 grams, 80 grams, etc. Okay, so this is just an example. So you are sometimes given both components, but sometimes you're given only one. So if, let's say, this water is not here, then you need to know that water will complete the percentage. Okay, you'll see that more as we go along. So the question here is, at 20 degrees Celsius, what is the maximum solubility of sugar in water? So first we have to find the temperature at 20 degrees. So this is 20 degrees. And it crosses this point at the line. This is the solubility line. And this corresponds to about, that looks like 64. Okay, 63.5, 64% of sugar in this water. So at 20 degrees, you can have 63.5% sugar plus the remainder will be 100 minus 63.5 of sugar. Maximum. Okay, you can put less sugar than that, but you can't put more. What happens if you put 70% sugar is you will form a sugar solution and there will be sugar gathered at the bottom because this cannot dilute anymore because it has exceeded the limit at 20%. So look at this line. Obviously, if you go up, if you heat up the solution, it is able to take in a little bit more. Okay, at boiling temperature, it can take a lot more. Okay, compared to at 20 degrees, it's about almost 20% more in terms of weight. Okay, and with the difference of temperature. So this is how we read this phase diagram. You have temperature and you have the composition of the phases. And we can read how much can you put a certain solute inside this solvent before it starts to form two phases. So to the left, it will still be a liquid solution. It will be a syrup because sugar plus water, you get syrup. But if you exit this, you will get what I drew here, which is liquid solution here, solid sugar at the bottom. Okay, so now you have to start learning about salt water and syrup. But we will apply the same concept to solid solutions. Okay, so let's look at some phases related to solid solution. A phase is a homogeneous portion of a system that has uniform physical and chemical characteristics, including microstructure. So in solid phases, we divide it further into BCC, FCC, etc. Okay, I think I've mentioned this before. Normally you will have gas and then liquid and then solid. But here we focus on solid, actually a bit of liquid and solid, but we divide the solid further. FCC, BCC, etc. Okay, so FCC is its own phase. BCC is its own phase. And then we have phase equilibrium, which is equilibrium where you have more than one phase present. This is a good example. Okay, a phase equilibrium is when the two phases exist in a system. Okay, two phases means two of these phases. FCC and BCC, FCC and liquid, BCC and liquid, etc. As long as there's two or more than two. Okay, here free energy is minimum. That means there's no reaction. System characteristics are constant over time. The phases are not changing. Okay, so example of this phase equilibrium. Just now we put up to 65% of sugar in water. Okay, and then you add more water. What will happen is you add more sugar. What will happen is any added sugar will remain as solid, which is what I have drawn a couple of times. You get this. So this is the phase equilibrium. That means you have two phases, 1 and 2, existing in an equilibrium manner. That means they are not reacting. They can be as they are without changing. Okay, constant characteristics. So this is easy to understand, and you should know that phase equilibrium can also happen on solid-solid solutions. That means FCC plus BCC. Okay, maybe you mix an alloy together, two different metals. You mix it, there's a limit that it can stay in the same phase. If put more, maybe it will have two phases present. Okay, that is phase equilibrium in solids. And there's another term here, metastability. Metastability is actually when the system is not completely in equilibrium. I'm talking about this system. There's some micro changes, but we are treating it as equilibrium anyway. Okay, so metastability is a common term because equilibrium cannot actually be reached. So we are treating it as equilibrium, ignoring the micro changes. So here is written very slight and often imperceptible. We cannot perceive the changes in the characteristics. Okay, so here let's look at phase diagrams of pure substances. Just now we were looking at sugar and salt. So now let's look at real phase diagrams of pure substances. Pure substance can exist as solid, liquid, or vapor. They are separated, the phases, by boundaries. So we have two examples here. We have a water diagram and a pure iron diagram. So this is for water. I'm sure you have seen this before. Okay, this is a phase diagram of water. Here we have pressure and temperature. So we know that there's a triple point at slightly above 0 degrees where solid, liquid, and vapor can exist. This is specific to water. Okay, and of course, if we increase the pressure, the line will slightly be different. And let's say we fix the pressure. Fixing the pressure at atmospheric pressure, you get a solid at 0 degrees. Slightly after 0, it will be liquid. And then if you go up to 100 degrees, it will be vapor. Okay. Now, so this is the liquid portion. Past this line, it will be vapor. So atmospheric pressure should be above this. Yeah, I'm sorry. It should be above this. So let's say